So, hello everyone, and welcome to this extra session organized for the NPTEL course Basic Environmental Engineering and Pollution Abatement. The course has been instructed by Professor Prasenjit Mondal from IIT Roorkee and myself, Chaitra Borkar, a Ph.D. student from IIT Delhi, and I will be conducting this session today. So, I will be going through a brief overview of the lectures that were conducted for the 12 weeks of the duration of this course, followed by the discussion of the numerical questions uh, given to the students during the assignments that were taken up for each week. The solutions are already provided to you. However, if there are any steps that you may feel you do not understand how the solution is computed using those steps, so this may help you in understanding the exact steps that were taken to get to the solution. So we start with the overview for the first week. So first week was the introduction of this course. So it dealt with the environment and its components such as biotic or abiotic component and the different cyclic processes such as the water cycle or the carbon cycle or the phosphorus cycle for the different elements. So these are certain restorative cycles which restore the vital resources that are needed for the survival of the species on the planet, and to some extent these are responsible for reducing the pollution as much as possible. However, if these cyclic processes are not able to reduce the pollution or are not able to replenish the resources to a required amount, there can be a possibility of certain irreversible effects on the environment, and because of that, a lot of pollution can be generated, or the sustainability of the future generation can also come into jeopardy. So the next lecture dealt with the ecology, environment, and biodiversity. So the different components of ecosystem, how they're interrelated through food chain or food web, that was discussed, and the stability and the biodiversity of the ecosystems. Next, the ecosystem services and its risk, part one. In that, the risk due to inferior quality of the resources, the risk due to the conservative nature of the pollutants, which different factors were discussed: bioaccumulation, bioconcentration, biomagnification factors, and the residual transmission of diseases. Also, the ecosystem services. So, this is the ecosystem provides the species living in it, a number of services, such as as you can see in this diagram, the provisioning services such as wood and fiber, genetic resources, energy, or regulating services which keep a check on the pollutants being emitted into the environment. So the global climate, microclimate, flood control, uh, pest regulation and all, and the cultural services such as recreation, religion, education, identity, etc. So different services an ecosystem provides, and it becomes a responsibility for the species living in it, uh, uh, mainly the human beings, that we need to preserve the environment so that the excessive human activity does not hamper the functioning of this ecosystem. So next, the risk and hazard were in that sense. Risk and hazard were discussed, and the risk analysis, management, and communication. So how much uh, percent of pollutants that we can work with, the so that the ecosystem does not come into any harm. The second week dealt with the pollution types and sources. So there are different types of pollution based on the atmosphere, based on the environment they are emitted in. It can be into the air, or it can be into the soil, or it can be into the water. Uh, Different based on the medium they are exposed to. Other types also include, such as liquid waste, solid waste. Based on the corrosion also you can differ the pollution types. And different sources of pollution can be either domestic sources or industrial sources, or it can be point sources or diffuse sources. So and the pollution from industries was also discussed. Next, the impacts and consequences of the pollution. So, due to different types of pollution, such as water, air, soil, or noise pollution, the different types of pollution cause different impact. And one of the major impact that it has caused is the global warming phenomena and the ozone layer depletion. Next, the transmission of these pollutants through the air medium and the water medium was discussed. So, firstly, in transmission of air, the air pollution dispersion. Here we see a schematic for the plume of the flue gas flowing out of the industrial chimney or stack, and how much should be this height of a chimney, so that the plume which is or the flue gas which is emitted out of this chimney is at a certain height, which does not, so that the contaminants in this flue gas does not reach the general public living around the industry, and does not hamper the environment in an considerable way. For that we saw a model equation which gives us the uh, height of the plume rise. So this is the actual height of the chimney, and plus the height of the plume rise, you get the effective height stack. And next, in the transmission in water, so how the pollutants are transmitted from the source to the species living into the environment, that was discussed. And in that we saw the modeling of the dissolved oxygen in the water. So how the as the contaminants are emitted into the water body, you see a increase in the biochemical oxygen demand, because then there is more oxygen needed to treat these to reduce treat these contaminants via the microbes that act upon it. And the dissolved oxygen then decreases, as we see through the oxygen sag curve. However, there is a phenomena called the re-aeration through the environment, which replenishes the oxygen inside the water. And as the re-aeration increases, the oxygen sag curves increases and the biochemical oxygen demand decreases. For the third week, we saw the environmental quality and standards. So we understand that the pollution is bad for the environment, it's dangerous for the species living inside it. However, we need to know what levels of pollution that can be that are prevalent, as well as what levels of pollution that can be withstood, that can be mm, that can be uh, that can be permissible, so that what level of contaminants emitted into the air or the water or the soil are permissible, so that there is no harm which is caused to the environment. So in that respect, ambient air quality and standards, as well as the water quality and standards were discussed. And the for air, different contaminants from the industry, such as the oxides of sulfur and oxides of nitrogen, which are emitted, and carbon monoxide. So, what should be the permissible limit for them, so that it does not cause any nuisance in the environment nearby, as well as the water, which is, if it is a drinking water, so what should be the quality of that water? It should be odorless, it should be colorless, it should have least suspended and dissolved solid as possible. And Also the irrigation, water use for irrigation. So in that sense, two factors were discussed. One of two factors out of different factors was discussed, and which was the sodium absorption rate and the residual sodium carbonate factor. So using that, you can know how if the water is fit to use for irrigation. Moreover, for one of the water quality standards can be the hardness which is present in the water. So because of the different salts of calcium, magnesium, you can get hardness uh, the in the water, and which can cause the depletion in the plumbing or piping that we use to store to transport water. And because of because of that, there is a loss in the ability of water to produce the lather from the soap. And this hardness can be of two types, which is permanent hardness or temporary hardness. And uh, for the standards for the industrial emissions and effluents was also discussed, and the noise standards for noise pollution as well as the vehicular pollution. So vehicular pollution from the automobiles, it can the automobiles can emit oxides of nitrogen, carbon monoxide, different hydrocarbons, as well as oxide of sulfur in some limits. So a check on that, as well as the particulate matter. So a check on that is necessary, so that the pollution is kept in control. Next, now we know what can be the permissible limits. So how to check for a sample if it has uh, how to find out the concentration in a sample taken from air or soil or water. So different instrumental analysis such as electrochemical, chromatographic, and spectroscopic analysis were discussed. And in that, we discussed the gas chromatography and gas chromatography coupled with mass spectroscopy, then FTIR, which is Fourier transform infrared spectroscopy, and UV spectroscopy were discussed. Next, we now know how to calculate the concentration, how to measure the concentration using different instrumental analysis. However, how to sample the air, polluted air, or the polluted water, or polluted soil. In that, we discussed different sampling methods for air, water, and soil, and saw the for air specifically the stack sampling, because this is the diagram for stack sampling for a circular stack, and we see at different positions we need to sample the flue gas which is passing through the stack. Um, Next was for air, we saw the different sampling measurements, parameters, analytical methods, and bacteriological measurements. In that, we saw uh, a computational model which can tell us the growth of the microbes in the water, uh, and how fast the colony can grow. Next, for the sampling and characterization of solid waste and soil, we saw the sampling methods, different sampling methods such as quartering or making a V notch. Next, the characterization based on physical and chemical methods. So, in chemical methods, as the solid waste has agricultural solid waste has different components in it, cellulosic or hemicellulosic or lignin type. So for those as well as the other components, we saw how to calculate the amount of these components in these solid waste, as well as the energy content of this solid waste. So the solid waste has to a large extent carbon compounds in it, and these carbonaceous compounds have the ability to be combusted and generate energy. So the utilization of the solid waste to generate energy can be done, and which can give us and in that sense different parameters such as high heating value, low heating value were discussed. And and how to measure the heating value of these component of these material using the bomb calorimeter was looked at. Next, the different environmental laws and regulatory framework implemented in India as well as worldwide were globally were discussed. So, the different environmental laws and acts that are implemented in India through the years, the implementation as well as the revision based on the development in the technology or development in the circumstances. So that was discussed, followed by the regulation framework which is implemented in India, which includes the Central Pollution Control Board or the State Pollution Control Board as well as the Ministry, uh, which looks after the environmental laws. For the fifth week, we looked at the air pollution control. So, different contaminants can be emitted into the air, which can be of gaseous form or the solid form, which are particulate contaminants. So, for the typical air pollutants and their composition in the air were discussed, and the process equipments, the processes as well as the equipments for the removal of pollutants were discussed in that. Firstly, the gravity settlers were discussed. This is the schematic for the gravity settler, and the different design aspects, such as the settling velocity of the particles, as well as what should be the length of the settler and the depth of the settler, based on that was discussed. Then the removal of for the equipments for removal of pollutant, we saw the electrostatic precipitators and fabric filters and their design aspects. Followed by the design aspects discussed for cyclone separator. And for the removal of pollutants as well as the gases components, the scrubbers and the absorption phenomena, as well as the devices used for that were discussed. And the control of specific gaseous components such as gaseous pollutants such as sulfur dioxide, NOx, and carbon dioxide emitted into the air were discussed. And the purification of air was also looked at. Next, for the sixth week, we saw the treatment of surface and groundwater for drinking water generation. In this, different sources of drinking water and the need for their treatment. So, different sources can generate drinking water, which has pollutants of different degrees and different types. So, the need for the treatment does arise so that the drinking water is fit for consumption, and based on that, the treatment of surface and the groundwater is implemented, and the different household filters that can be used, such as activated carbon or reverse osmosis, was discussed. The special treatment methods included disinfection. So this is the schematic for the treatment of the surface water. So firstly, surface water goes through a screen which removes the relatively bigger particles that can get entrapped into the screens, followed by the coagulation, so that the particles get accumulated together, and the flocculation, such that they are uh, suspended into the water, and sedimentation for the settling of these particles. Next, the filtration removes these particles, and sedimentation settles the uh, bigger particles which have gotten accumulated, and the filtration removes the finer particles, followed by the disinfection through either chlorine or ozone, and then the storage, and then distributed for the consumption. The groundwater treatment includes the rapid mixing, followed by the reaction basin, where coagulants or flocculants are added. Next, the settling tank, in which sedimentation occurs, and recarbonation, so that carbonates are present in the water, which are vital for the drinking water. And next, the rapid sand filter for removal of fines, and then the storage, and then to the distribution systems. So different treatment schemes for the domestic as well as industrial wastewaters were discussed. So, in that, the on-site disposal, which is a septic tank, and these sewage treatment, these are for the domestic waste, and the effluent treatment, the common effluent treatment plants, are used for the industrial waste that they were discussed. The process flow sheet for them were discussed. Next, in dividing the treatment method or treatment process of the surface of groundwater into different components. So firstly, we looked at the primary treatment equipment. So in that, different equipments that are used are bar rack or grit chamber, and followed by the equalization tanks, so that the consistency of the solid waste is uh, maintained, and the sedimentation tank. So this is for the primary treatment, and different types of settling and the design aspects, as well as the different types of settlers and the flotators. Next, for the secondary treatment processes, uh, a, a, a an introduction to these processes was looked at, in which aerobic processes or anaerobic processes, lagoon systems, or upflow anaerobic slush blanket reactors, and the biofilters were looked at. For the seventh week, the continuation of the secondary treatment processes, and in that we looked at the different equipments that are used for secondary treatment of the wastewater. So in that we looked at the activated sludge process and the modeling and design aspect of it, in which we modeled the mass balance equation to get the retention time, or the uh, cell retention time, and cell residence time, uh, and in that, this activated slur process, basically is an aerobic process which use oxygen to treat the polluting components in the wastewater. And next, the trickling filters, as well as the upflow anaerobic sludge blanket reactors and the lagoon systems, their design aspects were looked at in the second lecture of the seventh week. Followed by the advanced secondary processes. So these are the processes which are used to even further treat the the wastewater, which included the sequential batch reactor, the granular activated sludge process, and the membrane bioreactor. So these are the schematic for those. So this is for the trickling filter, this is for the UASB, this is for the SBR, and this is for the GASB. So the granule of the granule this granule has different regions, which has the outer aerobic layer, middle anoxic layer, and the anaerobic layer in the middle. So and this is UASB. Next, in the advanced secondary processes, we looked at the phytoremediation and phycoremediation. So phytoremediation is using the plants or the trees to treat the pollution, or to reduce the polluting components in the air, either the air or the water or the soil. And phycoremediation is the use of the certain algae which can remove the pollution from the different mediums. Next, in the advanced secondary processes, we looked at the microbial fuel cells or the microbial electrolysis cells. So microbial fuel cell creates the wastewater and generates the electricity as well as the cleaner water. And the microbial electrolysis cell uses the electricity to generate a purer form of water. So after the advanced secondary processes, we moved on to the tertiary treatment processes. In that, we looked at the adsorptive filtration. This is the diagram for the adsorptive filtration, in which this is the adsorptive filtration column, and this from this point to this point, it is the adsorption bed. So This is for the zero Earth floating, and as the wastewater is passed through uh, this column, we see that the mass transfer zone increases and goes towards the bottom. And as the leading edge of the mass transfer zone reaches the bottom of the column, we call it the breakthrough point. And based on that, the different design aspects are discussed. And next, in the tertiary treatment, we saw the different membrane processes and the modeling of the different types of membranes, or based on the pores which are there, and the mechanisms for the transport in the different membranes. And one more tertiary treatment process is the advanced oxidation process, which use the hydroxyl radicals to treat, which is an oxidant which oxidizes the contaminants which are present in the wastewater, so that we can remove these pollutants from the wastewater. So the ninth week was about the different sludge types, properties, and the need for the management. So um, now we treat the wastewater, and the sludge can be generated from either the primary settling or the secondary settling. So this sludge is basically the solids which are present in the wastewater which have been removed, and the sludge can have some moisture content in it. So sludge, primary, secondary, as well as tertiary in some respect. So different sludge types, their properties and the need for management. So different types of wastewater can produce sludge having different degrees of pollutants, which can be very harmful to some extent. So the need for their management, how do we dispose that, or how do we manage the sludge? And the sludge treatment, in that we saw firstly the thickening, uh, so remove as much as water as possible, then digestion, then conditioning, then dewatering and drying, followed by the disposal. One more aspect of composting of the sludge was discussed as well. Uh, in the sludge management, we looked at the anaerobic digestion, its mechanism, and the different digesters that are used. Next, in a series of the industrial pollution in grossly polluting industries, we looked at different industries and what sort of pollution it generates, and how to manage that using the treatment plants or different management methods were discussed. So in that, we firstly looked at the sugar industry. So sugar industry, we saw firstly looked at the process flow sheet which is given here, and we saw the different process elements that are used to generate the sugar. And in that, we looked at the different sources of wastewater that can be generated, or waste solids, and the different flue gases that can be emitted into the air, and the different sources of noise pollution. So, for the different sources of wastewater, how can we design an effluent treatment plant, so that the effluent which is coming out of this ETP has the permissible limits of the pollutants in it, and the solid which is generated, such as the bagasse, how it can be used for cogeneration. So cogeneration is basically using this bagasse to generate the steam which can be used in the boilers to generate the electricity. So the management of solid waste, the treatment of the wastewater, as well as the treatment of the solid of the flue gases which are emitted into the air, and the noise pollution were dealt with in this lecture. So the next industry in this series of industrial pollution control in GPIs, we looked at the distillery. Uh, so distillery basically uses the molasses, uses molasses to in India, basically, molasses are the raw material to generate the alcohol. So we looked at the process flow sheet, then the sources of wastewater, then the treatment methods and the ATP flow sheet, and finally the sludge management. Next, for the industrial pollution control in the GPI 3, we looked at the tannery industry, and tanneries are basically for producing the leather from the animal skin or hide. So in that, we looked at the process flow sheet, which involves the treatment of this hide and the treatment of this hide to remove the hair or other other components in it, and refining it to form the finished leather. So the different sources of wastewater here and the treatment methods, followed by the ETP flow sheet and the sludge which is produced, how to manage that. And the treatment, as this wastewater as well as the sludge contains a lot of chromium ions in it. So it is basically, the sludge is taken for the disposal through landfills. And next, for the pollution control in the petroleum refinery and the petrochemical industry. So this is the process flow sheet for the petroleum refinery, and the petroleum refinery is converting the crude oil into the different usable petroleum products such as the gasoline or kerosene, or the aviation turbine fuel, or the diesel, and as well as the natural gas. So the flow sheet for the refinery industry were discussed, and the different sources of wastewater from the different components, followed by the treatment methods. In that, the ETP flow sheet, which is a detailed ETP flow sheet, which has the primary methods and the secondary methods and the tertiary method to generate the waste, to generate the treated wastewater, which has the permissible limit of the pollutants, and the sludge management for the refinery industry was discussed, and in the petrochemical industry, the process flow sheet and the sources of wastewater were discussed. Next, the next industries that were discussed for the 10th week were paper industry, the fertilizer industry, and the copper smelter industries. So the paper industry generates a lot of wastewater, and how to manage that was discussed, and how to treat that was discussed. And fertilizer industry generates a lot of solid particulate waste, which is emitted into the air, or the gaseous waste, and the wastewater, different streams. And in this flow sheet, we see for a urea production process in a fertilization industry, we see different uh, dust streams are emitting out of from the different components in this process flow. So how to manage that was discussed, and the copper smelter industry, which produces the copper metal. So how to manage the pollutants which are emitted into the waste gas streams, or the particulate pollutants which are emitted, how to treat that were discussed. The 11th week saw the solid waste and the hazardous waste management. So 11th and 12th week are quite recent, so this the overview will be really brief. So in that, we looked at the solid waste and the hazardous waste management. So the different solid waste classification, routes for the solid waste management, the landfill. So landfill is a very it's a almost a final resort to the solid waste, so that to manage the solid waste, the different management of the hazardous waste and the waste plastics. Uh, in this week, we also looked at the different methods to manage the solid waste. The different methods are incineration, in which the use of oxygen to combust the solid waste to generate energy, and to reduce the pollutants in the solid waste. to reduce the pollutant, to reduce the solid waste basically. And next, the gasification. So gasification produces gasification uses a limited oxygen supply as well as steam to reduce the solid waste as much as possible and generate energy. And next was the pyrolysis, which is basically uh, mm, heating of the solid waste in the absence of oxygen, and which generates solid, liquid as well as gaseous uh, components. Next, for the 12th week, we saw the air pollution management, and in that we looked at the air pollution abatement plan. Firstly, we need to formulate a plan based on the environmental based on the pollution situation in the environment, and look at the emissions that are present, pollutant emissions that are prevalent in the environment or the air, and based on that the permissible limits need to be set, and accordingly the abatement plans need to be formulated, and need to formulate a framework that keeps the check on these abatement plan, that how they are implemented, and they are or whether they are implemented successfully or not. So in that, air quality management process cycle were discussed, and the air quality management in India, the legislative history for the pre-internet era, internet transition era, and the internet era were discussed, and in that, NEMP, which is the National Ambient Air uh, Quality Management Program, were discussed, and CAAQMS, which is the Continuous Ambient Air Quality Management System, were discussed, and this CAAQMS is used to generate the air quality index. So air quality index is a very effective communication tool, which basically condenses this lot of this data which is generated, which is the continuous ambient air emissions. So this continuous form of data is condensed into a single number, which can tell us the air quality of the ambient air, and the how the AQI is calculated in India. So that was discussed, and followed by the management of the special category waste, so biomedical waste, so waste which is generated from the hospitals, their collection, their treatment, as well as disposal, and the e-waste. So e-waste is a new concept, a relatively new concept as compared to the other types of waste. So because of the generation of a large amount of electronics and electrical devices, so if they are not in use anymore, or so how to dispose of that, that was discussed. The impact of these e-waste, also this e-waste have a number of valuable elements in them, such as copper, such as platinum, such as gold. So how to firstly collect these e-waste and treat them so that the extraction of the valuable resources can be done, and followed by the recycling. So this was the overview of the lectures that were conducted for this course. Now we look at the numerical questions that were given for the assignments, the current assignments in this course, and we look at how the solution, how we come to the solution using the steps that were involved. So second assignment had this numerical question, which is find out the air to fuel ratio, mass by mass, required for complete combustion of a liquid fuel. The average formula is C6H13 in an internal combustion engine. So this is the average formula of the fuel C6H13. We need the air to fuel ratio for complete combustion. So for combustion of the fuel, we require air, and air has O2 and N2. So, and O2 is 21% and N2 is 78%. So, if we know how much oxygen is required, we can find out the N2 required, and then finally O2 plus N2 gives us the air required. So firstly we write the balanced equation. So how the balanced equation comes out is, you take 1 mole of the fuel C6H13 plus some O2 plus some amount of N2. So air has, suppose air has 1 mole of O2. Some mole of air has 1 mole of O2, and how many moles of N2 will be there? So if we say that O2 is equal to 0.21 of air in O2. So we can get N of air, which is 1 by 0.21. And how many moles of N2 will be there? So N of N2, so it is 0.78 of N air. So we get 0.78 by 0.21 into 1. So basically 78 by 21 into 1. So this 78 by 21 comes out to be 3.71. So if uh, 1 mole of O2 is there, so 3.71 moles of N2 will be there in that air. But we don't know how much air is required. So we write here X. Okay. And next, this is the reactant side. Now we know in the product, when combustion occurs of a hydrocarbon, we know that carbon dioxide, some moles of carbon dioxide will be generated and some moles of water vapor will be generated. And as N2 is not being oxidized here, it is considered as inert. So some moles of N2 will be generated. So how many moles of carbon dioxide are there? So firstly, we need to balance the carbon atoms. So in the reactant side, it is 6 carbons. So here we write 6. In the and now the balance of the hydrogen atoms. So in the reactant side, it is 13 hydrogen atoms and it is H2. So we write 6.5. So that 6.5 into 2 gives us 13 on the product side as well. So now the hydrogen and the carbon atoms on the reactant as well as the product side are balanced. Now from this we can find out how much O is required. So here we see that 6 into 2, 12 plus 6.5 of O is required. Okay, but we here we see it is O2. So we divide O atoms. O2 will be 12 plus 6.5 is 18.5 divided by 2, which comes out to be 9.25. So these many moles, so X is equal to 9.25. So these many moles of air is required. Okay, so we need to, so this is in mole basis. We need to find out the air to fuel ratio in mass basis. So for 1 mole of C6H13, 9.25 moles of air are sorry, 9.25 moles of oxygen are required. Okay, so because the total moles will be O2 plus N2, so 9.25 1 plus 3.71. So these will be the moles of air. So how you calculate the mass by mass? So from moles to mass, you multiply with the molecular mass. So this is the detailed solution given here. I'll use this formula given here. So 9.25 is the moles of oxygen, and you multiply that with 32, which is the molecular weight of oxygen. And this will be the moles of nitrogen, 9.25 into 3.71, and you multiply that with the molecular weight of nitrogen, so you get the mass of the air from here. Okay, and divide it with the mass of the fuel. So how you get that is multiplying the molecular weight for 6 into 12. So 6 atoms of carbon are there, so 6 into 12, and 13 atoms of hydrogen are there, 13 into 1. So you divide this and you get 14.786, which is equivalent to 14.8 here. The correct answer here is the second option, 14.8. Next, in the second assignment, we looked at the numerical question, which is CO2 is emitting from a 75-meter high industrial chimney of diameter 0.25 meter to the atmosphere, 1 bar pressure, on a clear summer day. Wind speed at 10-meter height from the ground is 3.8 meter per second. Calculate the effective stack height. Assume B category stability, P value of 0.15. The stack gas velocity is 7.5 meter per second, and the temperature of stack gas and ambient air at 80-meter height are 50 degrees Celsius and 25 degrees Celsius respectively. So the here in this question, the height of the stack is given, which is 75 meters, and we need to find out the height of the plume rise, so that we get the effective stack height. So the relation for the plume rise is this relation given here. So and for that we need to find out what will be the wind speed at the 75 meters. We are given the wind speed at 10 meters. So using this relation, we find out the wind speed at the 75 meters, which comes out to be 5.14 meter per second. So using this relation and taking the proper units, we find out the plume rise, which is 0.566. We add that to the actual stack height to get the effective stack height, which is 7.566 meter, which is the answer here, the first option. Next question, mole fraction of aqueous glucose solution is 0.035. What is the molar concentration of glucose? So assumption, the density of solution is 1. So we firstly take the basis as 1 mole of solution. So this is the solution for this. So we see that for 1 mole of solution, if we have 0.035 moles of glucose, I write it as glucose, okay. And then how many moles of water will be there? 0.965. Just simple subtraction. So and we convert these moles of water into the volume of water. So how you do that is firstly multiply by molecular weight to get the mass, and then this mass is converted into volume by dividing by density. So you get the volume of the water, which comes out to be 17.37 milliliter of water, and using the unitary method. So in 17.37 ml of water, if there are 0.035 moles, So how many will be there for 1000? So it comes out to be 0.035 upon 17.37 into 1000. So this comes out to be 2.0149 moles of G, which denotes glucose, in 1 liter of water. So 1000 milliliter is equal to 1 liter. So this is the answer here, 2.0149, which is the fourth option here, 2.015. In the assignment 4, the numerical question was to determine the water equivalent of a bomb calorimeter 1.6 gram benzoic acid sample, which has the high heating value of 6318 calorie per gram, was used. The experiment produced a net corrected temperature rise of 4 degrees Celsius. The acid titration required 11.9 milliliter of standard alkali and 8 centimeter of par 4 5C10 nickel chromium fused wire was consumed in the firing. Determine the water equivalent of the bomb calorimeter. So this is the relation for calculating the high heating value of the bomb calorimeter, which has, this is the temperature rise, this is the water equivalent, and these are the different error terms which need to be extracted divided by the mass of the sample. So rearranging this equation, we get the water equivalent using this relation, and sorry, this should be water equivalent. So we get the water equivalent as plugging these values. So 1.6 is the mass, HHV is the 6318. These are the different error terms. Here E2 is not used, so this will be E1 and this will be the E3. Based on the material which is used, we find out the E3. And E2 is not there because here we are not given the information about the sulfur content, and divided by the temperature rise, which is 4, we get the water equivalent as 2534.775 calorie per degree Celsius, which is the first option here. In the fifth assignment, the numerical question was calculate the plate area of an electrostatic precipitator, removing 85% of particulate matter from the exit gas of a cement industry having 200 ppm of particulate matter. Assume the exit gas flow rate as 150 meter cube per second and the drift velocity of the particles as 0.11. So here we need to find out the plate area. So the plate efficiency based on the design aspects of the electrostatic precipitator has 1 minus exponential into minus of drift velocity Vms into the plate area upon the flow rate. So this is the relation used here, and sorry, VPM. And using this relation, rearranging this equation, we can find out the plate area. So we know the removal efficiency as uh, uh, collection efficiency or removal efficiency as 0.85, and the drift velocity is 0.11, and the units are maintained here. So this is meter per second, this will be meter square, and this is meter cube per second. So 0.11 into AC upon 150, and this is the flow rate, 150 meter cube per second, and we get the after rearranging, we get the plate area as 2586.98 meters square, which is equivalent to 2587 meters square, which is the second option. In the fifth assignment, in the continuation of the fifth question, the sixth question was in the question number 5, what change in plate area of ESP would be required to improve the collection efficiency from 85 to 99%. So now the collection efficiency is increased to 85 to 99%, but how much area needs to be increased for that? So assume the exit gas flow rate as for 150 meter cube per second and the drift velocity of particle as 0.11. So this is the relation again, and we just change the collection efficiency here to 0.99. Okay, and We then find out the area using this rearranged relation, which gives us 6279.77. But we need to find out the change in area. So the change in area will be subtracting the area which was there for the 85% collection efficiency, and we get as 3692.79, which is nearby this value, the fourth option. So the correct option here is 3689.78. Next question. The sixth question had for a continuous flow settling tank 3 meter deep and 55-meter long, what would be the flow velocity of water for effective removal of 0.03 millimeter particles at 25 degrees Celsius? The specific gravity of the particles is 2.65 and the viscosity of water may be taken as 0.01 centimeter square per second. So we know the dimensions of this tank. We need to find out the flow velocity, and we are given the properties of the particle as well as the fluid, and from firstly there we find out the settling velocity, which is Vs. We know the length and the height. From there we can find out the flow velocity. So how do you find that out? This is the relation given here, Vs into L by H. So a tank has flow velocity as this and the settling velocity as this. This is the H and this is the length. So firstly we need to find out what is the Vs. So you use the relation derived from the Stokes law, um, which is given here, which has the acceleration due to gravity, the diameter of the particle, the density difference between the particle as well as the fluid, and divided by the factor 18 and the viscosity of the fluid. So here we use this is the viscosity in Pascal second, or Newton per meter per second, but here we see that this is in centimeter square per second. So this is basically kinematic viscosity, which is mu by rho. So we are given here mu by rho basically, but we need to find out, we are given here specific gravity. So specific gravity is basically the rho of some solid upon the rho of the reference. So basically the rho reference is usually water. So the specific gravity is given. So how do you find out the rho s or rho p? Rho p will be specific gravity of the particle into rho of water. So rho of water is basically in the denominator itself, denominator of the denominator. So it gets into the numerator. So basically you only need to subtract the specific gravity and not multiply with the water here. But you need to change the unit of the centimeter square per second to meter square per second. So how you do that is multiply with 10 to power minus 4 factor. So we are given, we know the acceleration due to gravity, we know the particle diameter, we convert it to from millimeter to meters, and take the difference of the specific gravities, and in the denominator we have the 18 factor and the converted form of the kinematic viscosity into meter square per second, and from that we get the settling velocity as 8.09 10 to power minus 4 meter per second. Now we need to find out the flow velocity, and we use this relation as discussed before, and from there we find out the velocity as 1.483 centimeter per second by converting this meter per second value, which is the third option here. The sixth assignment had the numerical question as a circular sedimentation tank fitted with mechanical sludge removal unit is to treat 4.5 million liters of water per day. The retention time of the tank is 6 hours. If the depth of the tank is to be restricted to 3 meters, calculate the diameter of the tank. The capacity of the tank can be calculated as volume is equal to this relation d square into 0.11 plus 0.785 h, where h is the depth and d is the diameter of it. So here we know theta, which is the detention time. We know the relation for volume, and we know the flow rate. So from this, if we rearrange this, we can find out the diameter of the uh, cycling tank. So how do you calculate that? Is you firstly uh, change the units. If this is in hours and this is liter of water per day, so you can convert. So this is the solution given here. So firstly, you convert the flow rate into liters per hour or meter cube per hour. Why? Because the dimensions are in meter as given here. The restriction is to the 3 meters. So here you plug in the h as 3. So firstly, you convert this 4.5 million liters per day uh, into meter cube per hour, which is 187.5 meter cube per hour. And now you know the 6 hours of detention time, and you use this relation V by Q, and the relation for the volume is given here, and you rearrange this equation to get the diameter as 21.36 meter, which is the second option here. The seventh assignment had the numerical question as a complete mixture activated sludge process is used to treat a wastewater flow of 2 million liters per day having BOD 5 of 250 milligram per liter. The biomass concentration in the aeration tank is 2500 milligram per liter, and the concentration of net biomass leaving the system per day is 70 milligram per liter. The aeration tank has a volume of 250 meter cube. What is the hydraulic retention time of wastewater in the aeration tank? So here you know the flow rate, which is 2 mLT, and which is 2 into 10 to power 6 uh, liter per day. And you know the volume as well, which is 250 meter cube. Now you need to find the detention time, which will be V by Q. So you use that relation, and here you convert this liter per day into meter cube per day, and divide the volume by flow rate. You get it as 1.125 days. A completely mixed, next question in the assignment 7, numerical question. A completely mixed activated slurry process is to be used to treat wastewater flow of 550 meter cube per hour having soluble BOD5 of 200 milligram per liter. The concentration of soluble BOD5 escaping treatment is 20 milligram per liter. So the design criteria are as follows, which are y is equal to 0.5, the k, which is the specific, which is the rate for the biochemical reaction, which is 5 days inverse, and the kd, which is the decay rate, is 0.05 day inverse, and ks, which is 80 milligram per liter, and the concentration of the MLVSS is 2000 milligram per liter. Compute the meal cell residence time. So theta c, and the relation for theta c from the modeling aspects is given here, and this is the relation, and we plug in the values maintaining the units here in mainly in the milligrams per liter here and here as well, and this is in day inverse, so that is okay. We get the value, this is kd, this is ksse, which is given here. Se will be 20 milligram per liter, which is escaping the treatment. Okay, so you plug in that and you find out the cell residence time as 2.22 days. In the assignment 8, the numerical question was find the water flow rate in meter cube per meter square day when it passes through a porous polyethylene membrane by a pressure differential at 70 degrees Celsius. The membrane has 30% porosity with 0.5 micrometer diameter pores and a tortuosity of 2. Pressures on either side of the membrane are 400 kilopascal and 100 kilopascal. Assume the membrane is 2 microns thick and flow is fully developed laminar flow. At 70 degrees Celsius, the viscosity of water is 0.42 centipoise or 0.00042 Pascal second, and the density of water is 1000 kg per meter cube. So we know the relation for the water flow rate is given here. This is the porosity, and this is the tortuosity. This is the pressure difference, and this is the thickness of the membrane. This is the diameter of the pores. So we plug in the values maintaining the units here. So here this is in Pascal second. However, we need to find out the water flow rate in meter cube per meter square day. So Pascal second needs to be converted to Pascal days. So you divide by 3600 into 24, and here uh, you get the value as 36160.71 meter cube per meter square day. Next question. The In the eighth assignment, the question was 100 milliliter solution containing 25 milligram per liter fluoride is treated with adsorbent doses, that is 5 gram per liter. The percent removal of the fluoride were 70%. Calculate the specific uptake. So specific uptake is the fluoride removed upon the fluoride removed amount, and this is the amount of adsorbent. This will be in milligram and this will be in gram. So milligram per gram is the unit here. So the base is given here is 100 ml of solution. However, the concentration given here is 25 milligram per liter. So in 1 liter, it has 25 milligram of fluoride. So in 100 ml or 0.1 liter, it will have 2.5 milligram. Moreover, the adsorbent dose is per liter as well. So for 1 liter, 5 gram of adsorbent, and then for 0.1 liter, how much will it be? 0.5 gram. Okay, and here we need to find out the fluoride removed. So 70% were removed. So 0.7 into 2.5 milligram upon 0.5. So we get the specific uptake from here. So this comes out to be 0.7 into 2.5. It comes out to be 1.75 upon 0.5. We get the answer as 3.5. I understand this question was doubt for a number of students as they were not getting the proper answer here, but however, the correct answer here is 3.5 milligram per gram. And this is the detailed solution given here. The ninth assignment had the numerical question as a sedimentation tank is treating 5 milliliter per day of sewage containing 290 ppm of suspended solids. The tank removes 60% of the suspended solid. Calculate the weight of sludge produced per day, assuming moisture content of the sludge is 90%. So the correct answer here is the second option, 8700 kg per day. How it is calculated, with you see using this solution. And firstly, we need to understand that sludge has, in this case, sludge has removed suspended solid plus moisture, and this is 0.1 times or 10%, and this is 90% or 0.9. Okay, so firstly, we need to find out the inlet suspended solid rate. We know the rate for the uh, sewage, and which is 5 into 10 to power 6 liter per day. We convert, and then we find out, multiply it with the concentration of the suspended solid, which is 290 milligram per liter or ppm, which gives us 1450 into 10 to power 6 milligram per day. We convert it to kg per day, which comes out to be 1450 kg per day. So the suspended solid removed. So it tells us that 60% of the suspended solids are removed. So that will be 0.6 into 1450, which gives us 870 kg per day. And the SS removed are basically 0.1 into the sludge produced. So from here we find out the sludge produced, which is 870 upon 0.1, which is 8700 kg per day. Next question in the assignment 10. In an industrial biogas plant, food waste is anaerobically digested to produce biogas. The slurry contains 10% of solid food grains. The elemental composition of the food grains on a dry basis is C 50%, H 5%, O 35%, and N 10% mass basis. Around 90% of the food grains are converted to biogas, and all the converted hydrogen forms methane. If the flow rate of the slurry is 3500 liter per day, calculate the rate of biogas. And biogas is basically carbon dioxide plus methane. So we need to find out the rate of biogas production. So firstly, we need to understand this problem in a detailed manner, as a lot of data is given here. So flow rate is given in liter per day. So for 1 day operation, we know how much volume is dealt with. It is 3500 liters of slurry. Firstly, we dissect the slurry in the form as slurry, food grains, and different components, others. So food grains may have different components such as C, H, O, and N. And here we see this is 50%, this is 5%, this is 35%, and this is 10%. So slurry, first we need to find out the mass of slurry. From there we can find out the mass of food grains and the mass of different elements which are present in the food grain. So liter 3500 liter of slurry, we assume here the density as 1 kg per liter. So the mass of slurry is equal to 3500 into density, which is 1 kg per liter. So we get 3500 kg of slurry dealt in 1 day operation. So the mass of food grains will be 10%. So 0.1 into 3500, which is 350 kg. Okay, and from here we can find out the CHON. So 50% gives us 350. 50% of 350 gives us 175 kg, and this is 5%, so 17.5 kg. This is 35%, so 122.5 kg, and this is 10%, so 35 kg. However, not the complete amount of the CHON are converted to biogas. CHO are converted to biogas. So only 90% is converted. And one more information given here is the all converted H forms methane. So we start here with hydrogen. So firstly, we need to find out the converted H. So it will be zero point 0.9 into 17.5, which comes out to be 15.75 kg. If I'm not wrong, let me just check. Yeah, 15.75 kg. And we know this elemental reaction relation as C plus 4H gives us CH4, if you look at it in the element point of view. So 12 units of mass. So this is the molecular weight. 12 units of mass of carbon plus 4 units of mass of hydrogen gives us 16 units of mass of methane. So here, from this relation, we can find out if 4 units of mass of hydrogen gives us 16 units of mass of methane, then how much 15.75 kg of hydrogen will, how much methane will 15.75 kg of hydrogen give us? So 4 gives 16. So how much will give 15.75? So that will be 15, using the unitary method, 15.75 into 16 by 4. This comes out to be 63 kg. Now we know how much of methane is used. Okay, so from here we can find out how much of carbon is utilized for CH4. So C for CH4 from here will be, we are given here 63 kg, and again this relation comes into play. So if 16 units of mass are produced using 12 units of 16 units of mass of methane are produced using 12 units of mass of carbon, so how much carbon will be used for producing 63 kg of methane? So we use this relation as 63 into 16 by 12. Again, unitary method is utilized here. Sorry, it will be 12 by 16. My bad. It comes out to be 47.25 kgs. So now we know C utilized for methane. And now from there we can find out, so converted C is used for C for methane and C for carbon dioxide. Okay, so converted C will be 0.9 into 175, which is 157.5 kg, and C for CH4 we know as 47.25 kg. So we can get this value as 157.5 minus 47.25. 110.25 kgs. So this is the carbon utilized for CO2. Now again the elemental reaction C plus 2O can give us CO2. So this is 12 units of mass. This is 2 into 1632 units, and this gives us 42 units of mass, 44 units of mass. So if 12 units of carbon give us 44 units of CO2 in mass basis, so how much will give us, how much of 110.25 kg of carbon will give us CO2? So we use the unitary method here again, and here we use 44 by 12, and then we get the value as 404.25 kg. So now we know CH4, it is 63. Now we know CO2, which is 404.25. We just add this, which comes out to be 467.25 kg, which is the correct answer given here, third option. So this is the solution, how you compute this answer, and the detailed solution is given here for your reference. Next, we look at the numerical problem given in the assignment 11. So it had the question as, in a fixed bed gasifier, airflow rate and feed flow rate are 15 n meter cube per second and 12 kg per second respectively. The feed material does not contain any sulfur, nitrogen or chloride. The syngas contains carbon monoxide, which is 40%, carbon dioxide, which is 2%, hydrogen gas, which is 30%, and methane, which is 5%, and acetylene, which is 2%. Calculate the rate of production of syngas in n meter cube per kg of the feedstock. So in the week 11, we were given the relation for the rate of production of syngas, and this relation is shown here. So we know the air flow rate, and we need to multiply that with the 0.75, which is the mole percent of the nitrogen which is present in air. Then in the denominator, we subtract all the other components of the syngas, which are CO, CO2, hydrogen, methane, and acetylene, and multiply it with the feeding rate in the denominator, and at the same time maintaining the units here. So this is n meter cube per second and this is kg per second. So here we get the value by plugging in the values and maintaining the unit as 4.702 n meter cube per kg, which is the second option here. The 12th question in the the 10th question in the assignment 12 was that the ambient concentration of CO2 in a city is 500 ppm volume by volume on a particular day. Express its concentration as milligram per liter ppm in mass by volume of air. Assume STP. So the correct answer here needs to be expressed in milligram per liter. So the option here should be milligram per liter basically. And the correct answer here is the last option, 0.98 milligram per liter. How you calculate that is using this relation. So firstly, you are given. So firstly, we need to understand the meaning of ppm volume by volume. So ppm is parts per million. So 500 parts of CO2 in 10 to power 6 parts of air. So if you take the basis, some basis, I take the basis as 1 meter cube of air. So using this basis, we can say that 500 meter cube of CO2 in 10 to power 6 meter cube of air. Okay, and then how much in 1 meter cube of air? So If 1 million meter cube of air has 500 meter cube, then 1 meter cube will have 500 into 10 to power 6, 10 to power minus 6, sorry. Meter cube of CO2 in 1 meter cube of air. Okay, so this is the volume of CO2 in 1 meter cube of air. Now, from volume of CO2, we go to moles of CO2. How you do that is using PV is equal to nRT relation, ideal gas relation. So we know the we know the STP condition as 273.15 Kelvin and pressure as 1 atm or 1.01325 into 10 to power 5 Newton per meter square or pascals. So we plug in this value. R will be taken as 8.314, which is given here. So these values are plugged in here, and we know the volume. So we can find out the moles of air in 1 meter cube of air. So we get the moles of CO2 in 1 meter cube of air as 0.0223 moles. So now we know the moles of CO2. How then you need to calculate the mass of CO2. How you do that is multiply with molecular weight. So the molecular weight of CO2 is 44 grams per mole. So 0.0223 into 44 gram per mole in 1 meter cube in 1 meter cube of air gives us 0.981 gram per meter cube. So this is in gram per meter cube. Now you need to multiply. Now you need to divide by 1000 to get gram per liter, and convert this gram into milligram. You basically get 0.981 milligram per liter, which is the fourth option, the correct answer. Any questions relating to the uh, numerical problems or anything? You can pose the questions up till the up till the exam is being conducted, and uh, we will be happy to solve your doubts. Thank you everyone for viewing these live session or the recorded versions, and thank you for your feedback as well. I'll now go ahead and close this session for today. Thank you everyone.